This conference.
Okay, the practical part of how to train our deep neural network we see today. Same for sentiment analysis. So here I'm going to take some few matrices. X is TF-IDF matrix. And capital Y for binary labels. And our network size is like this. One input layer, three hidden layers, and one output layer. So this is what we are going to take into this. So for data reading and a TF-IDF related conversion function, all these things you know. In all our previous examples, we have used this code. From a scalar dot feature extraction dot text from this TF-IDF vectorizer. And also we need numpy. Still some errors. Here, not from import. Okay. Now, based on the shape of this input matrix, we have to define the size. How to verify the shape? X dot shape. Five rows, six columns. That means number of input neurons should be. So here the network construction, weight matrices. I'm going to take W1. Actually, your input matrix size should be 5 by 6. What about W1? 6 for input neuron, 9 for first hidden. That's why 6 by 9 we need to take it. And W2. This is the first hidden and second hidden layer. For the second hidden layer, I'm going to take 11. First hidden has 9. That means the W2 should be 9 by 11. And between second and third hidden layers, one more weight matrix. For the third hidden layer, I want to keep 9 neurons. So size 11 by 9. So that is last hidden layer. After last hidden layer, one more layer will be there, output layer. Binary problem, that's why only one. So you guess how many? 9 by 1. Already input matrix ready, label matrix ready, weight matrices we need to create it. 4 weight matrices we need. Look at this. np.random.seed. Fix some value. W1 you are going to take. np.random.random off. 6 by 9. What is for 6? Number of neurons in inputs. 9 for number of neurons in first hidden layer. Like that. Left side is for previous layer, or the right side is for next layer. On that way, how to imagine? To keep some values as positive and something into negative, multiply and minus 1. Otherwise, every value will be positive value only. That in between 0 to 1 only. Same style, W2 size. I repeat the same statement. But size has to be modified. 9 by 11. The next W3. 11 by 9. The last W4. 9 by 1. So initially these are random weights. After completion of training, what is expected? Matured weights. Okay. So what do you mean by matured weight? It should have minimum error. Understand? When compared with all the previous errors, with the latest weights, with the matured weights, the error should be minimized. Okay. So for that normal for MSC function, y minus y cap square. For this entire thing, average dot mean. So this is valid expression if the given arrays are numpy arrays. If those are normal Python lists, this expression is wrong. Okay. One more function for activation function. Here we are going to use the activation function sigmoid. Here X is dot product of input matrix and weight matrix. I think internet disconnected. Sir, are you getting voice?
No, get sir.
Okay, now you are getting right. Okay. Still we need another function, derivative. Here x is what in this moment? That is a sigmoid of input matrix into weight matrix. That means the result of activation function. Okay, here x is result of activation function. Here x is dot product. Input matrix and weight matrix. Okay. Here the expression x into 1 minus x. That's it. Return this. Got it? One more I am going to write a special function here. Define predict. Define predict. Input matrix capital W. So here in this case, that x is input and capital W is a list of all weight matrices. In this moment we have only 4 weights. In another moment you can have 10 weights. Understand? I'm passing a list of all weight matrices. Okay. Let's say some sample example. Capital W equal to is a list of W1, W2, W3, W4. Maybe in another program you can use 10 weight matrices. Understand? Every time you cannot change that predict function. Okay. Just one predict function we are having. In the first iteration, what it should be, sir? In the first iteration, first activation function is what? X and W1. X, W1 for that sigmoid. In the second iteration, the result of previous iteration into W2. Understand? For this, what we are doing, observe. R is equal to sigmoid of X comma W1. If I fix like this, W, now here capital W is a list, right? There are 4 weight matrices in that list. Perform a loop for that. For small w in capital W. For small w in capital W. For 4 elements, 4 times the loop will be running or not. Before this for loop, R is equal to X. Think that R for result matrix. Please consider high, sir. Now here in the loop, R is equal to sigmoid of R into R dot of small w. Anything understood? Just I will try. All of you consider it here. My function is this one. Okay. Tell me iteration by iteration, sir. Iteration number 1. Before that iteration, what is R value? Input matrix. In the iteration number 1, what is R value? Sigmoid of sigmoid of x dot of w1. Sizes, please. X size what? X size 5 by 6. W size what? 6 by 9. Total, what is the result? 5 by 9. Okay. Again, that result is kept into R only, right? In the second iteration, tell me. In the second iteration, R is equal to sigmoid of previous R. Previous R, which is 5 by 9. Comma, W2. Now, this time W value is what? W2, right? Dot of W2. What is the result? R size 5 by 9. W2 size 9 by 11. 9 by 11. Correct? 5 by 9 into 9 by 11. 5 by 11. Right? Next, sir. In the iteration number 3, R equal to sigmoid of, again R into W3. Tell me the size. 5 by 11 into 11 by 9. 5 by 9. In the last iteration, what is R value now? Same sigmoid of R into R dot of W4. What is the value? 5 by 9 into 9 by 1. Total 5 by 1. We are passing 5 rows. 5 predictions you will be getting or not. Okay, instead of writing 4 statements, suppose if the weight matrices are 4, you are writing 4 statements. If weight matrices are 10, you have to write 10 statements. Instead of doing that, this for loop will solve your problem, right? Got it? Yeah. So this technique we are applying. After completion of for loop, return R. So at the time of calling this prediction, you have to pass first initial input matrix and list of all weight matrices. That's it. This will take care. Got it? Next, I'm going to write training, the code for training. Initially, I'm fixing convergence. And previous error. Of course, up to now, no iterations. That's why previous error initially I kept it as 0. Whether training is completed or not to confirm it, 1. For I in range of for I in range of, let's say 1 lakh. Give some bigger count. Even though training completed in middle, loop will be breaked whenever it meets the convergence. Come on, sir. Already have predict function. But predict function is giving you what? Last layer output only. Understood or not? It gives you last layer output only. But to know that to do the predictions of previous layer errors and deltas, I need independent hidden layer outputs. but still I want to take the help of that predict function. First L1 I want. Take help of predict. In this moment, input matrix, capital X, weight matrix, a list of course, in that list only a W1 I am giving. Next L2, predict of, still, can I say like this? Can I say it like this or not? Or man, just look what you are passing. Input matrix, initial input matrix, and list of weight matrices. You want last layer output means in the list, keep all the weights. If you want second layer output, keep only first two weights in that list. You can call it like this, or simply L1 is already ready for you, right? We can go like this. Both are correct. What is another way? Just I am commenting this. L2 equals to predict of initial and W1 comma W2. Understood this? Same style you tell me L3. Predicts L2 comma W2. Last L4. Predict L3 comma W4. Here 3, right? Yeah, 4. Right. Now E4, error 4. Capital Y minus. This is overall error or residual error? Residual error. Y has 5 by 1, L4 has 5 by 1. 5 by 1 minus 5 by 1, another 5 by 1. So for each row, what is the prediction error it will give you? What is the overall error? That thing I am saying as CE. C equal to MSC. MSC of Y comma Y cap. Y cap is your network prediction. Network prediction is in L4. Got it? What is the difference between previous error and current error? Absolute of PE minus CE. At each iteration, how much error is decreasing also I am interested, sir. At each iteration, how much percentage of error is decreasing? I want to know that. Suppose the previous error 100, sir. Current error 80, sir. That means 20% decreased or not. So I want that information. Got it? Yeah. So for that, the formula, the percentage of decrement. What is the formula? Current value minus previous value divided by previous value into 100. Current value minus the previous value divided by previous value into 100. Suppose the result minus 10, sir. Result minus 10 means what? 10% decremented. Result plus 10, sir. 10% incremented. Okay. So, but in our gradient, what we are expecting at each iteration? Error should be decreased. Okay. Yeah. So for every 15 iterations, we will print that, or for every 50 iterations or 100 iterations. If I equals percentage 100, equals to 0. Then print error is CE. How much decremented? I am giving PER value. Both the things at a time we are printing. So if that difference is less than or equal to convergence, training completed, then break it. If difference is less than or equals to given convergence, the number of iterations, how many also I am interested to know. That's why I plus 1. Immediately 1. J already 0, right? Okay, here we keep 1. Let's make it 0. Up to L1, L2, L3, L4 only activations. Weight adjustments are pending, right, in the backwarding. Come on, write the adjustment for the L4. To adjust that for L4, L4 is because of W4. To adjust the W4, we need delta 4. Come on, delta 4. Delta 4 equal to derivative. Current error, which is E4, into derivative of the result of that layer. What is the result of that last layer? L4. Activation result of the last layer. Okay, next delta. To know the delta 3, first I should know error 3. First you have to do error 3 prediction, E3. Current delta dot of current weight matrix, W4 transpose. Right? We are not doing anything new, sir. All these things, whatever the work you did for the simple neural network, the same thing you are doing. But number of layers more, that's it. Come on, now E3 is ready. Delta 3. Current error, E3 into derivative of. What is the current output? L3. Now you can predict E2. Delta 3 dot of W3 transpose. Now delta 2. Error 2 into sigmoid of W2. The last error 1. Delta 2 dot of. Here also you can observe these steps are keep repeating, right? You can perform a loop. Or else for all the deltas you can write a function, one more function like predict. If I call that derivative function, if I call that delta function, automatically how many weight matrices are there, that many deltas should be produced. On that way you can develop one more function to make it reusable code. Okay. Delta 2 dot of current weight matrix W1. Now last adjustable, which is delta 1. E1 into sigmoid of. We are very sorry. We should not apply sigmoid. We should apply derivative. Derivative of. Here not the transpose. Here mistake. Here L2. Here L1. E4, E3, E2, E1. All the things are ready. Now only adjustables are produced. Still we did not adjust it. Come on, adjust the W1, sir. W1 plus equals to previous input matrix X transpose dot of current delta. For W2, input please L1 dot of delta 2. For W3, dot of delta 3. For W4, input L3. L3 transpose into dot of delta 4. All weights are adjusted. Before going for the second iteration, it's all the happening in first iteration. Before you go for the second iteration, direct the current error into previous error. After completion of your loop, if j equal to 0, here we did not break it, right? After you make j as 0, if the convergence is met, break the loop. Otherwise, unnecessarily, 1 lakh iterations will happen. If j equal to 0, still after completion of 1 lakh iterations, still j value 0 means training not done. Just give that confirmation message. Training not completed. Now we are going to train this model. There are some errors. Shapes 5 by 11, 9 by 6 not aligned. Somewhere we have kept into the mistake. In the matrices sizes, 6 for input row, right? 9 for hidden, first hidden, 6 by 9, 9 by 11, 11 by 9, 9 by 1, correct. MSC, correct. 1 divided by 1 plus. For the sigmoid, what we have passed here, already the dot product only we are passing. Okay, no problem. Sigmoid is okay. Derivative, L1, L2, L3 we are passing. Let me verify what is the mistake. At line number 20, 25, E2, E1. Look at E1, sir. Delta 2 dot of, here the mistake, sir. W2. Have to say W2. Okay. Delta 2 dot of W2. Otherwise, size not matched. The matrix multiplication rules are not matched. Okay. Yeah. Now I am running the same thing. Observe the training. Look at the second column, sir. Every time is what is happening here. Here, look at this second column. Of course, in the first iteration, divided by 0 is anything is infinitive, right? What is the formula we kept for that percentage? Current value minus previous value divided by previous value. In the first iteration, previous value is 0, right? Anything divided by 0? Infinity. Second iteration, after 100 iterations, for every 100 iterations, you are printing minus 8. That means 8% decreased. Once it reached 8% decrement, after that 1.2 decreased. After that 0.61, 0.31. Now onwards, slow decrement is happening. Finally, after how many iterations? 9,424 iterations. Convergence is met. That means training is completed. Now within our W, matured weights are there. Okay. Where are our W's? Capital W. Capital W is a list of 4 weight matrices. Weight matrix 1, weight matrix 2, like this. You can check one by one. This is weight matrix number 1. Just observe the shapes. Dot shape. 6 by 9. W of 1, 9 by 11. W of 2, it should be 11 by 9. Sorry. And W of 3, 9 by 1. W of 3 means that is the fourth one. 0 to 4, 0 to 3 only. Now I am doing prediction. Already did a predict function. Now no need to say L1 equal to L2 equal to L3 and L4 equal to. Already you have a predict function. My predictions y cap equal to predict of. What is your input matrix? Capital X. Your weight matrices? Capital W. This W contains 4 weight matrices. So that you will get a prediction. Prediction should be 5 by 1. Check that 5 by 1. The values will be very deadly close to zeros and ones. 0.99 means that is very deadly close to 1. Same style 0.002, 0.001, these are close to 0. Generally, the basic machine learning models are having the benchmark is 0.5. 0.5 greater than, 0.5 less than. Suppose a probability that you are a male is 0.49 means or 0.51 means. Understand, sir? 0.51 is the probability that you are a male means 0.49 is the probability that you are a female. The closeness is very high between male or female in decision making. Okay, but in case of deep learning, the predictions will be the deep neural network training trying to approximate to the actual levels, trying to be deadly close to the actual levels. On such way, the weight adjustments will happen. So for accuracy testing purpose, you have to convert all these things into what? Labels, binary labels. How to? Y cap. Y cap of y cap greater than 0.5. Make them as 1. Y cap less than 0.5 as 0. Now all the values are zeros and ones. Now you can test your accuracy. Already accuracy function you know. Just for recalling purpose, I'm redefining. Define ACC. Y cap. The comparison result matrix y equal to y cap. True and false. Those matrices will be written. From that, just take only true values. R equals to true. How many are true? Dot size divided by number of elements y dot size into 100. Just return this expression. Now test the accuracy. ACC of your capital Y is actual labels, Y cap is your predicted labels. Already the predictions you transformed into binary arrays. Of course, 100% accuracy. In this way, the deep neural network will get trained. So how it is better than simple neural network? What is the advantage? Of course, in simple neural network also we got 100% accuracy. Of course, data is simple. If data is having complex patterns, then you can feel the difference. Because of more weights, more knowledge will be derived. Got it? That too, what is the thing? What is the basic advantage within this? In one hidden layer, if I keep more number of neurons, but activation function is only one. Because of multiple hidden layer, one activation function will be the input to another activation function, so that more transformations, more complex predictions can be solved out. Getting the point? So in tomorrow's session, I'm going to migrate this code to polynomial predictions. Suppose in our previous text data, for NLP purpose, what are the text document we have taken? How in sentiment analysis, what are the two labels we have, sir? Positive, negative. Got it? And positive label and negative labels, only two things. But some customer is saying that, okay, the product is good, that is positive, you can understand. Okay, the service is bad, negative, you can understand. But so some customer is saying that no comment. One of the customer is saying that no comment about your product. Okay, or else I don't have any idea. Now these two, the last two customers are what? Neutral customers. Now I want to classify these things as a positive, negative, neutral. Got it? Suppose I collected some of the documents. We think that within that 100 documents are positive, 100 are negative, some other 50 or 60 are neutral. So whenever a customer has posted a review, automatically application has to understand whether it is a neutral or positive or negative. Now what is the challenge here? Number of classifiers are not 2, greater than 2. If number of classifiers are greater than 2, this is called polynomial classification. If it is a binary classification, simply you are going for probability base. Less than 0.50, greater than 0.51. But if it is polynomial, 2, 3 classifiers, 4 classifiers, 5 classifiers, how you do? Okay, that techniques tomorrow we will be learning. So same sentiment analysis going to with a deep neural network. Same sentiment analysis with a deep neural network. Okay, that to do more than 2 classifications. So if it is more than 2 means it can be of anything. 3 not a problem, 10 not a problem. Once you know this technique, right? In next session we will deal that. Okay, all of you, let's meet tomorrow.